to have with us today Dr. Manuel Juárez. Dr. Manuel Juárez completed his PhD in animal production from the University of Seville in 2007. Previously, Dr. Juárez completed an MBA and a DVM and worked in research labs in Italy and Ireland. He also worked in the private sector in Finland and Spain. In 2009, Dr. Juárez arrived to Canada as a postdoctoral fellow, and 2 years later, he became a livestock phenomics scientist at the Lacombe RDC. Dr. Juárez coordinates the Agriculture and Agri-Food Canada Livestock Phenomics Program, linking livestock genomics and phenotypic research focused on meat production. Dr. Juárez applies a holistic approach to evaluate the interaction between genetic and environmental factors in order to quantify their relative contribution on animal performance, carcass, and meat quality traits. Breeders can benefit from being able to select and sort animals based on current and expected market conditions. His goal is the optimization of livestock production systems to maximize profitability while maintaining or enhancing carcass and meat quality. Thank you for being with us today, and the floor is yours.
Thank you. Thank you for inviting me. And I can start with the presentation. How do you see the screen?
It's perfect.
Yeah. Okay. Well, so you see the title of my presentation is a bit wide, but what I intend to do is give you a bit of an intro to my understanding of livestock phenomics, how it links to genomics and genetic selection, and a couple of examples of how we have done things in Lacombe. And then from there, I will end the presentation giving you my view of how I would like to see research moving forward in the future on this area. So let's see, the presentation was to behave. There we go. You all know quite a bit about this interaction between genotype and environment, how that leads to the final phenotype, all those traits that we can measure on the live animal or on their products. That's a bit more complex than the traditional genetic by environment. You have the genotype space, but then you have the external and the internal environments plus the internal phenotype and external phenotype. So an internal phenotype could be the fiber types in the muscle, and the external phenotype could be the tenderness of the muscle. And you have all those different factors complicating our lives, but also making it more interesting on the research side. So the field of phenomics has a couple of different definitions. I like the one that says that calls it the systematic acquisition of high-dimensional phenotypic data on a genome-wide scale, or the measurement of phenoms as they change in response to genetic mutation and environmental influences. In summary, it's a holistic approach to the collection of phenotypes in both the live animal and their products, and it's an interdisciplinary field. As you will see at the end, you know a bit about many things, you don't know enough about any of them, but you collaborate and then you get results. And the reason for the need of an independent field called phenomics comes from a justification that has been relevant for many years now. This is from 2010. But basically what you have to see is, I'm old enough to remember when genomics research was always the limiting factor for every study. Genotyping a few animals was so expensive, but that started changing, and as of today, usually the limiting factor is getting the phenotypes. The phenotypes are very expensive, and even if you can genotype 5,000 animals, getting the live data and the carcass data from that many animals would be very expensive for any single project. So there's a need to be able to generate phenotypes in a different way. The approach actually didn't start in livestock research, it started in psychology. In psychology, they understood that all these interactions between the environment and the genotype and all the different traits that you could measure was more complex than originally stated. So they started working on this field many years ago. In the plant research world, is also quite common. Maybe not as much in livestock, but in livestock, one of the things that is increasing the the need, or maybe increasing the adoption of phenomics approaches, is the increasing popularity of precision livestock farming. So many of the tools that we are seeing for precision livestock farming can be linked directly to phenomics. So you see here, this is a common representation of what precision livestock farming looks like. But if you increase one level into that graph, you see that you can start combining the pedigrees and all the data from the omics from those animals. You can follow not just the live animal, but also the final product. You can integrate that in a livestock phenomics approach that will enable genetic selection and validation on new phenotypes. And then you can go back to the farmer and continue working with this precision livestock farming approach. But all the data that all these sensors are collecting are phenotypes, right? So all environmental data that we also need in phenomics. So it's a very real link between precision livestock farming and phenomics, and I think we can both fields leverage the advantages of each other. I like to represent phenomics this way. I think this includes pretty much all the information that explains the flow. So you have commercial producers from which you can collect environmental information and all the phenotypes that are available from either the live animals or their products. From then you can integrate that with data from all the omics, proteomics, genomics. With that information, you don't create just new genotypes, you create new phenotypes that then can be tested first by breeding groups and then back to the commercial producer, and there we go again. Right? So that's the life cycle of the data collected in livestock production. And at the center, we have this data integration analysis that is key in order to be able to put all that information together. But the three pillars of livestock phenomics are the phenotypic data, the environmental data, and bioinformatics. So we are going to see some examples of how that applies and how I approach it from my program. So the first case study is going to be on beef. And well, I will explain more when we go forward. We had a research question coming from the grading system in Canada, and I guess in all around the world, but especially in Canada and North America. Limit yield is the main trait that we are basing our grading system on, beside marbling. So limit yield is measured on the loin, collecting some linear measurements, and then those are used in a prediction equation. And with that information, we estimate how much lean or sellable meat with the system from the US we will have in a whole carcass. The accuracy of those predictions is not the highest, but that's what has been used for a long time. And right now we have modified a bit to homogenize with Americans. But that's still the system. Linear measurements on the loin, and from there you estimate total muscle, total limit yield in the carcass. Well, we thought that maybe there was a way of understanding how those predictions on the loin are impacting the rest of the carcass. As of today, there's no a real application for this information, but there are new grading systems. For example, in Australia, they have a system based on X-ray technology where they can scan the whole carcass and then they can identify how to cut the different primals. That technology is not in North America yet, but it could arrive here at some point. If that happens and we keep selecting based just on the loin without understanding what happens in the rest of the carcass, we may be at a disadvantage. So this was a PhD thesis for the now graduated Dr. Vipasha Sood at the University of Manitoba. And when we started, the first challenge was, okay, if we want to look at the genetic influence on all these different primals and their composition, we need large amounts of data. We need over 1,000 animals at least to start looking into this. So we'll have this crossbred population, and we need to have their full pedigree, their genotypes, as much environmental information as we can get, and then the phenotypes, which are not cheap phenotypes. usually the phenotypes that you want to collect for this kind of information would include carcass dissection, so taking each of the primals, separating lean, fat, and bone. That would be very expensive. You have to do in many animals because of just the carcass depreciation and the manpower. You need to understand the methodologies that have been used. You may have to work with people working on the animal science field up to meet quality. And you need to collect the tissue that you are going to use for the DNA analysis later on. So as a project from scratch, will have been very expensive and very complex and maybe hard to get funding for, because, as I say, it's not a priority as of today, but it could be one in the future. Well, here at Lacombe, we have projects running all the time. So I have been involved with several in the last 15 years, and I was able to create my program around all these projects and collect data in a way that could be used and implemented to answer questions such as the one in this research project. We are lucky here at Lacombe. We have facilities that are quite useful for this kind of research. We have about 400 cow herd, a crossbred population. We keep always the heifers from replacement heifers for our cow population, so they are all linked maternal side. We have our own feedlot, and then we have the abattoir where we can slaughter those animals. So every year, for the last 12, 15 years, we have slaughtered all the steers produced in our herd, plus the heifers that were not used as replacement. And we have been able to process them in a commercial manner, similar to a commercial abattoir. Then from there, we have across the value chain, we have people working from genomics to the eating quality of the meat, passing through grading, food safety, bioinstrumentation. So that creates, I mean, you in Guelph are very lucky. You also have the whole cycle over there, right? So, but that creates an opportunity to collect data from different areas and research fields. Most of our projects are on beef. We have some projects in pork, some in bison. As you see, we don't have 100% there. It doesn't count for 100% because we have other projects, sometimes in lamb, sometimes in fish. But in general, 50-60% of our projects are in beef. Now, so when I started my program, one of the first things that I did was look at these areas that need to be homogenized in order to collect phenotypic data in a way that you can apply later on. So many years ago, I started standardizing all our protocols so we could combine data from multiple projects. We created a common language for all the researchers, so everybody calls the same trait, the same name, and also we use the same protocols. I will give you some details about that later on, but for example, when you're talking about, I don't know, shear force, Warner Bradley shear force, you think that everybody would do it the same way, but people can be using different temperatures, different cooking methods. They can be using different cores, different speeds for cutting the meat. So we need to standardize, and I was able to do that here at Lacombe. We are small enough that work well. And then what I call deep phenotyping is when we look at phenotypes that are not commonly collected in other places, but we can spend more time and more resources into collecting those phenotypes. So I created a database, one for beef, one for pork, where I enter all this information from the multiple projects, including all the environmental information that we need later on to be able to correct any values in the large database. So thanks to that approach, we were able to access the database had around 5,000 animals, but we were able to collect over 1,000 animals who had all these things in common. All of them had been finished here at Lacombe using a common commercial diet, and they have been monitored regularly, slaughtered in the abattoir, and then graded, and blood samples have been collected for DNA extraction. We had standard protocols about what to do 24 hours after slaughter, from measuring shrink loss to, as I say, all the grading traits from fat thickness to ribeye area. and then the pH at different times. So the full grading that will happen in a commercial plant, plus some additional traits that we collect for our research approach. And then these 1,000 animals, or over 1,000 animals, had something that is uncommon, because up to this point you could say, well, there are other databases with that information, but we have more than 1,000 animals who for which we had scanned their carcasses individually, and we had cut the primals, as you see, chuck, rib, brisket flank, the shank, loin, round, and plate, and we had scanned them through our X-ray machine, our DEXA machine. This is an instrument that scans whichever tissue you place on the bed with low energy X-ray, and then it can tell you the amount of lean, fat, and bone without having to do a manual dissection. That's why we were able to combine this in multiple projects and without increasing the cost of the study. But at the end of the day, we had this information of composition of individual primals in over 1,000 animals, which is quite unique and not easily found anywhere else. Then all these animals, as I say, we collected blood at the slaughter. We also collected blood live in the farms in case there was some issue. We sent these samples to, originally it was a different company, but now it's Neogen. And we did the genotype with the commercial chip from Illumina and did all the quality control. We ended up with over 35,000 SNPs that were common to all of them after quality control. Then the first thing that we did was looking at production factors and how they were impacting the composition of the different primals. We had animals with implants and without implants, animals that went to calf-fed or yearling-fed endpoint production system, so backgrounding or no backgrounding. So we saw, as we expected, the implant impacted the composition of all the primals. When you use implants, all the primals become leaner, so they have less fat component. The production system had an impact, especially on the loin and the rib, a little bit on the shank, but well, the shank is less important. But the loin was impacted by that production system, the calf-fed versus the yearling-fed, with calf-fed being leaner in the loin, but not in other primals. So you start seeing already some differences of what happens on the loin and other primals in the carcass. We use some statistical approaches to try to understand how those factors were grouped. So we saw, as we expected as well, this is repeating some of the research that we had in the past. The British breeds led to more fat in all the primals and more marbling. The age at the slaughter and the backgrounding also led to animals with more fat, while the use of continental breeds like Simmental or the implants, hormonal implants, related closer to the lean traits. When we look at the other plot, we had the first and the third component of the analysis. We had that the loin is, you see, we have all the primals here grouped on the right, and the loin is a bit different. The loin and the shank, but especially the loin is a bit different. So although we'll see afterwards there were good correlations, this is always something to consider when you are doing your research or your selection just based on the loin. Then we started looking at genetic parameters. So heritabilities for carcass weight, cold weight were moderate. We had some good heritabilities for marbling IMF, estimated yield, a bit lower for the different primal cuts. But the interesting thing was the heritabilities for the primal composition were quite high for both lean and fat. Then in terms of correlations, we saw very strong correlations among the lean and the fat traits of the different primals, and negative correlations between lean and fat as expected. So the results were what we would have anticipated. So just from these results, you could say, well, the loin composition is well correlated to the composition in other primals. So, you know, you are doing the selection based on the loin, it should be okay for the rest of the primals. But then we went to the next step, that was GWAS analysis. And I mean, there are tons of results to look at, but you see, you look at this Venn diagram, it's a bit complicated. but I can summarize the main findings. We had 21 markers that were common to all the primals and estimated limit yield and everything else. But then when we look at just estimated lean yield, we had 138 that were not linked to any of the individual primals. When we look at the actual lean yield from our analysis, we only had 7 of them. Right? So, and then you look at the loin link, it has 44 markers that were independent just for the loin. So based on this and other results that we had, what we found is if you are doing your selection just based on the traits from the loin, yes, you are going to have a similar impact in other primals, but there are going to be a number of effects and a part of that selection that may not be impacting the other primals the way that you intended. So if at some point we get to the point where we are doing a grading system looking at individual primals, or if the individual primal prices change and there is quite a bit of focus on some of those primals by themselves, maybe the general grading system that we're using today should not be the only thing that we use for selecting animals for the next generation. So anyways, this is just an application of, as you saw, collecting data for many years and then being able to answer a question, a research question, without having to slaughter a single animal. We were able to do all of this without a project in which we had money to slaughter any animals. We just used that historical data and those historical samples that we collected over time. Okay, so that's at the end of the day, you don't care much about this result. That's what they want you to take away from the application of phenomics. You're going to see a similar case here now, but this time in pork. In pork, the situation is different. In pork, we have big variability in quality in the different primals, and that variation in quality can really change the value of the individual primals. You can have a belly that is quite firm like this one, and a belly that flops like the one on the right side. So the difference can be at 20% in price or higher. Same thing with loins, and same thing with ham and shoulders, depending on the market. We have been running many projects focusing on classifying these primals based on quality using different technologies, developing some technologies at our end, many of them high throughput technologies for research or technologies that the industry can apply. So this has been going on for the last, again, 12, 15 years. And I also created a database for pork where we entered all this information, and we collected blood from all the animals passing through our abattoir. So we have a database that is over 5,000 animals, over 2,000 of them we have the blood samples collected from and fully genotyped. So some of the technologies are on the live animal. We have sensors that can monitor from temperature to humidity, carbon monoxide, ammonia, vocalization from the animal. So really detailed environmental information. We have 3D camera systems to look at the composition of the animal still at the farm. We use thermography, so infrared, but also multispectral cameras from 2 different companies to look at the different changes in temperature, both for productivity and animal welfare. And we have individual feeders where we can weigh the animal and their diets every day in a routinary basis. Then we have worked with different technologies for grading the carcasses, but also for understanding deeper information in terms of composition in the primals and in the carcass. Right now we are finishing a project with 3D cameras, and we scan all our animals through our DEXA instrument. In terms of color is very important in pork. So we have worked on image analysis methods. We have worked with different colorimeters, and we have developed new color standards, both for research and for industry applications. Same thing for marbling. We have near infrared spectroscopy approaches. We have new standards. Well, these are not new. These were developed a few years ago, but we apply them constantly, and also image analysis applications. So some of these technologies have led to the development of different approaches. This is an example. This is a headset that is voice activated, and you can use to grade or to support the grading and the classification of pork loins real time in the farm or for research. We also had a project with the University of Guelph. I think Dr. Dan Tulpan is on the call. In that one, we were trying to create classification systems for the whole loin, for the back of the loin. And we have used similar approaches. Image analysis has become quite important in our field in the last few years. So same thing for hams and loins. We can measure different traits from total fat areas to different thicknesses and different important locations in the primal. And my research has focused quite a bit on the pork loin, because the pork loin right now is one of the most expensive cuts in a pork carcass, way more expensive than a pork loin. Everybody's eating bacon, not everybody's eating pork chops every day. So we came with, we passed from the traditional barbed method to two different iterations of barbed instruments that can measure in real time. We also work with technologies for near infrared technologies for iodine value. And we went even up to creating an automated system for belly classification that could be applied in commercial plants, and right now is being considered by some companies. So all that took us to a place where we had a large number of animals fully phenotyped, with phenotypes that are not commonly collected anywhere else. And at the same time, we had blood samples or genotypes from all those animals. So at this point, we have over 2,500 animals that were evaluated that way. Those animals all were provided by the same company, by Genesis. So we were able to approach Genesis and come up with an idea to use all that information to evaluate the possibility of using markers in the future that are of interest for potential buyers and different international markets. So we did some preliminary analysis last year, and we saw that the heritabilities of all those novel traits were moderate to high, so they had the potential for selection. We have now focused more on bellies and hams. Bellies because of the North American and the Asian market, and hams because some of these animals are sent to Europe for producing dry cure hams. And also because we saw that while the selection for pork in the last many years now has focused mainly on limit yield and sometimes on a bit of marbling on the loin, that selection has led to some potential quality issues in other primals, like the belly and the ham. When you are trying to reduce the back fat thickness on the loin, you are also impacting the fat content of the belly, and a belly that is very thin without much fat is going to be very soft. You're not going to be able to use it for bacon processing or for some other traits. But at the same time, we saw that some of the traits in the belly were positively correlated with the traits in the ham. So there's maybe a chance to create a line of pigs with high quality hams and bellies that could be used either in North America for the bacon production and in Europe for the dry cure hams. So we have actually two projects now. One is focused mainly on the belly with the ham as a secondary primal. And then we have another project where we are going to look at heavy pigs. So we are going to look at animals slaughtered at 125 and 150 kilos and see what happens when you are doing the genetic selection on animals at 125, and then the producers are taking them 25 kilos heavier. Is that selection that you were approaching or that you were preparing to optimize performance and quality in the product at 25, is that going to translate to 150? Are you going to lose efficiency? So that's what we don't know. We don't know what's going to happen with the quality of the meat. We don't know what's going to happen with animal welfare as well, because when you have those animals, well, you are going to have to modify your diets, most likely, different requirements, and you may also have to modify the transportation parameters for heat stress and any other potential issues. So that's where we are going now, but we can't do that because as I said, we already have 2,500, 3,000 animals with all that historical data. So now to answer the new questions, we only need to analyze that data and potentially create some small trials. But we had to create 3,000 animals from scratch for the research. That would take many years and large amounts of money. So those are a couple of examples. And now I have just 2 slides, and I may stop a bit here after this for some questions. But what I want to extract from those 2 examples and from the introduction about phenomics is this is how I approach my program. Right? My program is interdisciplinary, not only across programs, but also across projects. I would not be very lucky at getting funding if I went and I told them I want to collect phenotypes for the next 10 years to answer these potential questions. That funding agencies don't give you money for accumulating data for the future, right? So I have to work through multiple projects and through the whole value chain. I have seen some approaches where people are working on the life side, or people are working on the carcass and the meat, but really you produce animals to at least beef and pork. You produce beef cattle and pigs to produce meat. So you need to look at the meat. But when you are looking at the meat, you cannot forget that the wildlife animals making that possible. So we need to look at the whole value chain in a collaborative way. When we do this, something that always comes up is, well, what happens with the intellectual property? What happens with the authorship? What happens if you are collecting data from multiple places? Well, in my databases, each data point has a field with the name of the project that links to the PI. So every time that I extract data to get a publication, to do some analysis, I contact that PI and I say, hey, we are going to use your data. Are you in agreement? If anything comes out of this, how do you want authorship to include you or some collaborators from this project? So doing that locally hasn't been too difficult. But that's something to consider always. At some point, you have some papers that, you have 15, 20 authors, and that happens sometimes, but that's something that happens on genomics as well. I have been able locally to standardize protocols and our ontology, the way that we call the traits. So when we do shear force, we always do it the same way. When we do color evaluation, and when I say we, is myself and any other scientist working on different projects. Sometimes I'm not even part of those projects, but then information can come to the database for future studies, and we all standardize our protocols so that you can compare. And if there is any change, that's part of the environmental data that we collect. Environmental data is not just the diet of the animal or the temperature or the production system. It's also the methodology. As I say, if I'm measuring color and I'm using a Minolta, CM, whatever, versus another time that I'm using a different Minolta, I have that in my database. If I have changed the parameters, for example, the angle, the viewer angle in the Minolta, that's in the database. And that's something that I have missed in many databases that are mainly focused on genomics. So they have environmental data, they have the diets of the animals, they have some of these major traits, but then they are missing changes in methodology, they are missing the name of the person doing the subjective evaluation. All those traits, sometimes they are just corrected by creating contemporary groups. But in my view, sometimes that's not enough. You need to really have any detailed methodology in every kill, in every animal. Another approach that we have in terms of collecting these large amounts of phenotypic data is automation, bioinformatics. We have, as you see, tons of image analysis, other data points such as temperature and pH. Right now, in terms of having somebody measuring temperature and pH at 45 minutes, at 2 hours, at 24 hours, I have a probe that collects data every 5 minutes for 24 hours, and then we download the data. So automation is great, but then you need bioinformatics solutions because now you have too much data. Now you need somebody to help you summarize it, put it in a format that can be utilized later on. And even for statistical analysis, you can not often use the traditional approaches. But now when you are collecting that much data and you are collecting that many images, you need to have storage solutions as well, because you pass from having a couple of Excel files to having terabytes of data from each project. And it's good to have redundancy. It's good to have more than one place where you collect the data, because imagine you have spent 10 years collecting data and now your driver crashes and you don't have a copy anywhere. Well, that's terrible. So we tend to have our data in multiple places. And then when I talk about DNA and tissue banks, it's very obvious for everybody working on genomics, you need to have blood samples or tissue samples to look at the DNA, sometimes at the RNA, whatever, any of the omics that you may be working on. So for every of the animals that pass through my program, we have blood from the animals at the farm, and then we have blood at the slaughter. As the animal are being bled at the slaughter, we either collect blood or we collect a tissue from some tissue from the ear. So we have that double DNA. And I can tell you more than once, not for my projects, but for other people's projects, we had to use that double sampling to identify animals that were lost. The traceability was lost at some point. So having the two DNA samples is always good. But on top of that, I have created another thing that is what I have my DNA tissue bank, and then I have my just tissue bank. The tissue bank is where we collect meat from whichever muscle is the standard, usually the longissimus, the loin, and we freeze dry that meat and a piece of fat, so they end up in a very small vial. So if in 10 years somebody comes and tells me I need to run a project where I look at the influence of these genetic markers on mineral composition of the meat, I could go back to those freeze-dried samples, just run the mineral composition analysis. We already have the genotype. You don't have to run a new study just for that, right? So that's an example. Same thing could happen about different fatty acids or different other compounds that you could look in those samples. So not just tissue for DNA, also tissue for further quality evaluation in the future. Now, when we have all of that, then I don't work on genomics directly myself, but then I can integrate this information with those working on genetics, because it's going to be in a format that it can be easily, as I say, when we have the DNA and we have the phenotype, now you want to do any study like the ones that I showed you before, it's ready right away. We only have to do some verification, some cleaning, and there you go. You don't have to start producing animals from scratch. For me, in my view, if somebody asked me, what would be the future? How would you like to see this going on? I would like to do this in a way that this approach that I can do locally, we would be able to do nationally or internationally, right? So we have institutions like mine working for federal, provincial governments, colleges and universities, any other research providers, and the private sector populating 1, 2, 3 databases where we have standardized the protocols, the ontology, where we look at all these environmental factors together with everything from birth to meat quality, and everybody's collecting DNA and other tissues. And we have a system to share this information, to integrate it, and then to access it. So it will become a common resource for anybody on animal production, meat science, or genomics. So as I say, tomorrow you have a research question. I would like to know if these markers that I found in a different study are impacting the fatty acid composition in the subcutaneous fat of pigs. I can tell you, hey, I already have 3,000 data points for that. Do you want to data mine that before you slaughter a single animal? So in terms of efficiency, in terms of the animal care committees priorities, now in terms of reutilizing the animals, recycling, and all that, we will be on top. So this is what I would like to see at some point. We don't have that many research providers, neither on beef or pork in Canada. So I think that's something that could happen. And there have been some attempts, but I think we could go farther that way. Okay. So that was my time, I think. So I will stop now and answer some questions.
I appreciate your presentation. It was very interesting. If anyone has questions, you can raise your hands, turn on your microphones and camera, and ask questions. Okay, so Flavio has a question. Go ahead, Flavio.
Okay, can you hear me?
Yeah.
I know. Yeah. Thanks for the presentation. Really very interesting in the sense that everybody's trying to do this nowadays, and concerned about this integration. So I'm curious to if you could, Mano, describe to us which kind of support infrastructure you had to develop this database. So did you do this by hiring, let's say, postdocs, or you had collaboration with any department there, like say in the engineering department, that help you to develop these databases, the integration, the concept of how integrate the different equipment, right? The sensors and whatever you use there. Can you describe to us, because you accomplished, but you have already this system developed. So it'd be really nice if you could describe how difficult it was and the resource that you used.
Yeah. Well, sure, and it changed over time, right? So this approach, I started it even during my postdoc time, so that was 15 years ago. Then I was hired, my resources were limited, but I guess that's one of the advantages of working in a center that is relatively small. We had about, at the time, I think about 7-8 scientists working on this field. So we were able to coordinate. The first database actually had to hire externally somebody to develop the database in a format that was good for us. We have a large group of common technicians, and that's also an advantage. I have my technicians, so the scientists have the technicians, but then we have a core group. So all our meat cutters or our basic quality people work in a core group, and we have a person, a lead technician that coordinates that team. So together with that person plus the other scientists, I started developing this software and this process. Over time, we got more support. So right now we have 2 bioinformaticians at the center. One of them was hired recently and is going to be mainly focused on image analysis. We have another one that is more focused on large data and more on the genomic side. At Lethbridge, being at the federal government, we can access resources in other centers. So at Lethbridge, southern Alberta, we have a biostatistician that can also provide support. So I leverage all these resources. Then locally, I have different technicians trained on different techniques to extract the data from image analysis or from the other sensors, and it all centralizes through that lead technician. And we have one person in charge of the beef database, another person in charge of the pork database. And over time, we had to deal with some issues. For example, how to get information from the live animals in a consistent manner. It's hard to get the data from calving during calving because everybody's very busy. So we have a system where 2 months after calving, we go and we collect the data. And so it's been a process of over 10 years. And I think we are lucky here with our resources and the way that we can access the information. So I don't know if that's possible everywhere. Also, by doing this internally, the IP is not an issue because everything belongs to the Crown. Everything belongs to the department. So we only have to talk about authorship. If I were to expand my database and collect data as I do for some projects from the private sector or from a university, then that requires agreements, and I also have those. But that's more painful for sure.
Okay, thanks for describing, because it is a challenging, like very challenging task at university, for instance, because you have here many departments and colleges, different colleges, so it's trickier, I think. But we have a projects now that are trying to accomplish the same thing, more integration. And my last question, Manuel, is this external person or company that developed the database, once they finalized, you took over the maintenance of the database, or we still have a external person that does the?
So today we still access. I have a meeting with this person actually in 2 hours, because we are going to add some columns and we're going to modify some things. We still do it externally. It was just easier. We have the resources now locally to potentially use our local people, but because this person developed it from the beginning, it was just easier to continue going. But right now we have very small changes here and there. There are challenges both ways, because this I mean, we have been lucky that this person has moved on and is still available for making those changes. So in a way, sometimes we thought maybe having somebody internal would have been better, but internal people also move on their careers. We actually created our databases in an Access environment, and what we had is a front end. So in the worst case scenario, I can always go to the root code and change some things myself. Really, we use this person to create a front end that makes it easy for all users. But otherwise, it's simple enough that I could do it myself if I had to. Sometimes when you get too complex, then you can get in trouble in the future.
Yeah, I think you mentioned have redundancy of the database itself, where they start, but we have a redundancy of people able not to give support. Okay, I don't like to centralize the conversation here. Thanks a lot for your presentation.
Thank you. And I know there are many initiatives trying to do this centralization of data. I know this open access science, that we are all trying to get within the federal government. Sometimes that's challenging, but it's doable. So if at some point anybody doing any of these initiatives wants to contact me and see if we can exchange data, I would be happy to deal with the paperwork at my end.
Thanks, man.
Okay, thank you, Flavio, for questions. Does anyone has more questions for Dr. Manuel? Okay, then. Well, we'd like to thank you again for your presentation. It was very nice to have you here with us today, and we hope to have you in the future again.
Thank you very much.